Yesterday's session, we discussed about HBase, which is database on distributed environment. Database on distributed environment, right? Now, when I say distributed environment, the database will be able to expand. When I say expand, horizontally scalable. The data, physical data that is getting stored will get automatically split into blocks, right? So if I have a software which is trying to basically record the data in tables format, right? I'm storing that tables in this particular software, but ultimately it is nothing but data. So this software will expand as and how more and more data is getting into it. That means ultimately it has to fall on HDFS only, right? The data has to get spread across this. But here the data is getting split into 128 MB blocks. That means the tables that we are going to store in HBase, they will get split internally, and physically they are getting stored into different blocks. Right? That's HBase for us. It has auto sharding. We have master, that is HMaster. Then we have regions, or region server basically. And then within region server, we have regions. So master is like your name node. Region server is like your data node where regions reside. And this is nothing but your table. And when we talk about the files, physically, the files are getting stored in something called as H files. These are your actual files. Typically, the size is 1 MB. It is recommended to have H file size as 1 MB. So when we try to write the data, it first gets into memstore. This is a memory location where the file gets first loaded into the memory. And once it gets filled up, then the data in the memory gets flushed into H files. And this is what we've learned as part of HBase. Now, HBase is a column-oriented data or column-oriented software or table. That means when I'm trying to create a table, I can grow horizontally with as many as columns I can have, right? So there is no restriction. And here in HBase, schema is flexible. We are calling it as a table and we need to have data, right? So in HBase, we can also have unstructured data as well. And the data is getting recorded. If it is in tables, it is getting recorded in columns wise. And all we need to look at is the column key, right? Now, if I have to look at the traditional way of the businesses, the traditional techniques, we have database, but this database is RDBMS. We're not talking about NoSQL. We're not talking about HBase. We are talking about RDBMS software, right? That means we are using SQL programming. We're using SQL programming. So data is already there residing. The applications are connected here and applications generate data and that data is getting filled up into this. Now I want to do some kind of analytics. So what should I do? I cannot directly take the data by connecting to this database. If you try to write queries to query to extract the data and do some kind of analytics on top of that, then the load on this RDBMS is increasing, isn't it? The load on RDBMS is increasing. That means it becomes very slow. The performance gets hit, right? Performance becomes slow. So what we do to maintain the consistency in the data, to do a lot of analytics on this data, and at the same time do not disturb the RDBMS performance, we create a channel, or we can say pipeline, and we push or we retrieve the data into Hadoop. Big data environment. We draw a parallel system where all the data which is getting uploaded here gets pushed as and how it gets updated here into big data system. And within big data, either you use HDFS or whether you use HBase, you can use any other software also to store your data. But we need to push this data from SQL to Hadoop, right? This is always structured data. So Apache Sqoop was developed to achieve this import export task. It's not just importing from big data, importing from SQL to big data, but also to export the data from Hadoop to your SQL. Right? Both import export things are done using Hadoop. We call this as a data ingestion concept, where we want to pull the data in. Right? So business generates data using various applications, and traditionally this data is getting loaded stored in RDBMS softwares. But if you want to do real time, or if you want to do any kind of analytics, offline or online, we need to have a parallel system, right? So here we need to have a big data system. Yep. So we need to push the data from database to HDFS or HBase or Hive tables. Now that is done using Apache Sqoop, which is nothing but SQL to Hadoop and Hadoop to SQL. This was developed by Cloudera, right? And it was made open source in 2011. Sqoop is used to import data from external databases to Hadoop ecosystem tools, not just HDFS. That's what I was adding here, right? Not just to HDFS, but you can also add get the data from structured database to your big data environment. That's Sqoop's work. This is how you see. Now, Sqoop does not have any user interface. It's a command line interface. It only gives a command line interface. And you're going to write queries kind of a thing, high level procedural language kind of commands, which will allow us to pull and push the data from these two systems, between these two systems. Yes, Ashner, please go ahead.
Sir, sorry to interrupt. I just want to clarify something. Is this live from Windows because this is MySQL going to the Linux system? Or is this residing both on one Linux server?
No, it has nothing to do with the operating systems. We are talking about two softwares.
Yes, sir. I was just confused if this Sqoop is working. For example, we have one server that is Windows, the other server is Linux, and when we use Sqoop because it's MySQL, and then we import data from Hadoop, or is something like that?
Right. So let me explain that.
Yeah.
So we have, let's say, Hadoop cluster setup. Now for Hadoop, we recommend we go with Linux operating system, right?
Yes.
So here I have Linux. XFS is the file system. The database that we're talking about, RDBMS database, could be on a Windows system. Let's say it is a local system that you have.
Okay.
Now what I do is, from command line interface, all I'm trying to do is to connect the service that we have here, not the operating system. We are connected to this service, right? It's a software. It has connectors, it has APIs and all that. We directly establish connection from here to here. Underlying OS could be anything.
Okay, understood now, sir.
Yeah. So this command line interface is given for Sqoop, and then we write queries, import and export queries, to pull or push the data from RDBMS to HDFS or HDFS to Hadoop or Hadoop to RDBMS softwares. Now, when you write this command, a high-level code, ultimately the code has to get converted into map jobs and reduce jobs, right? That's the key feature of these products that we are talking about on top of Hadoop. All of them will convert whatever the high-level code that you are writing into map jobs and reduce jobs. By default, the products will convert thanks to Yarn. Yarn is yet another resource negotiator. This is the one of the components of your Hadoop latest versions, that is Hadoop 2.x, which allows any third-party application or project on Hadoop ecosystem to connect with map, reduce, framework, and get things done. Right? It is also achieving fault tolerance, parallelism, and all these features while you are importing and exporting the data. Now, how does it actually work? I'll talk about import. Export is very similar to what you understand here. Okay, same logic. So I'm writing an import command. So when I say import, it is basically you're going to write the command from HDFS or Hadoop environment to import data from SQL. Right? So import basically means pulls tables from RDBMS system to Hadoop. Okay, that is import. Export means from here to there. Each row that we are, each row of a table that we are trying to pull, right, is considered is equivalent to one record in HDFS. Okay, if I have a table, I have one row, right? This one row is considered as one record on your file in HDFS. Now, when you write the import command, this command is getting divided into map jobs, right? Map jobs, based on the size of the key value pair data that we are going to define, each map job is trying to pull that part of the data from your HDFS records. Your data is in HDFS, right? So it is trying to pull part of the data, right? Then map jobs creates a connection again with this database. So we have this database, right? So it connects via JDBC connector and then pulls the records. So one record in the table is getting entered into HDFS as one record, right? And here no reduce, we're not reducing anything, right? So no reduce task will be there, right? If I say export is also same thing. You first take each record or each row in your HDFS from your HDFS and then try to create table in your SQL, just reversing the order. So we do not have reduced jobs for import export using Sqoop. You'll only have map jobs. Now there is another tool called Flume, which is also popular. Flume is used to, right, basically extract unstructured, primarily unstructured data. Because for structured data, we have Sqoop, no problem. Right? The application is already there. It imports the data and exports the data basically from structured data sources. Right? Whereas Flume only deals with semi-structured or unstructured. It does not deal with structured RDBMS softwares. Sqoop is a connector base. You establish a connection using APIs that are provided to the database and pull out the data that is required from that system. Whereas Flume is an agent-based architecture. That means you will have an agent, you'll have a server here, you'll have an agent there, and the communication happens between agent and the server. Right? Better to work with offline data, and the data is stored in RDBMS softwares. This is the feature of Sqoop. Right? Whereas if you talk about unstructured and semi-structured data with respect to Flume, you basically can extract the data when it is actually getting generated, right? So live streaming data can be pulled in for processing, right? Now, Flume is event driven. That means when the record is getting generated at that instance, the code gets executed, right? So it is event driven. Whereas a Sqoop is not event driven. There's nothing like only when event exists, occurs, the data has to be pulled out. No, it's not event driven. Right? You have to manually basically write a code and pull the data. Now, for when you're trying to import, you're trying to load the data from external RDBMS softwares to HDFS. Right? So you'll be basically having one database and one HDFS source. Whereas Flume, it can extract data from multiple sources also. And multiple sources might be generating the data. So we will be able to extract data from multiple channels. Right? So this is basically at a high level, guys. We have a lot of such softwares. And we also will learn about Spark, which can do all these tasks that we are learning. Okay, let us try and understand Spark now. Apache Spark or Apache Spark. This is the most happening software right now in the big data environment. Or you can also talk about cloud environment. So we are going to try and understand the architecture of Spark. We are going to detailedly understand what are the various capabilities Spark has. Right? So let's proceed. So if I have to look at the history of Spark, it is actually made open source in 2010. Okay, even before you have Sqoop. Sqoop came in picture, or it was released in 2011. Here Spark is prior to that. But Spark initially, right, it was very, I should say, popular program or project or communities in the big data environment in Apache community. But it took time for everyone to actually appreciate the features of Spark. Right now, if you look into the cloud environments, cloud platforms, almost all the cloud platforms by default give Spark only for their computations, either Python or Spark. Right? So, what is the Spark? Why is it so popular or gaining so popularity? Right? So let's try and understand that. There are a few names given here where these people contributed in Spark development. Now it is owned by Databricks. Basically, they drive the progress. Spark, though it is an open source, it is managed by Databricks. Now, Apache Spark, from the definition perspective, is a interactive multi-step analysis tool. Okay, it's a tool which allows you to interactive, and you will also be having multi-step analysis, right? Now, when you try to execute any task in MapReduce framework, what happens is we have multiple map jobs which are triggered, right? When I say map reduce, multiple map jobs get triggered, right? And all these map jobs will run parallelly on multiple nodes to extract the key and value pair. And when it does, each map job is accessing the hard disk of all these individual nodes where the blocks, physical data is stored. So when I say physical devices, I mean physical hard disks, these nodes, they take time to get all the data read because you have to ultimately do a disk read, right? So it takes a lot of time, latency. You have seen that, right? In Apache Pig also we experienced that. It takes a lot of time to get one task executed, right? Now, how about getting the same task done in a split of a second at a rapid pace? Can I try and do that? Right? The idea is to get the execution done fast. First, when we had no big data solution at all, organizations were trying to find a solution to handle that big data. But as and how the demand is growing, data is big already, right? And if you do processing on top of that big data, processing will obviously be very slow. So can I improve the processing? Right? That's what Spark's objective is all about, and it does that very, very efficiently. Yeah. Now, how does it solve? It basically reads the data only once from your device, hard disk, where the actual physical data lies. It reads that only once. Yeah. So what happens if I have an iterative transaction to be done? All those iterative transactions are done without accessing the hard disk if your data is going and sitting in memory. So all you're doing is reading your data only once. Right? From your hard disk, you're reading your data only once. Yeah? So Spark tries to push the data into memory and then access the data which is there in memory for your iterative transactions. Your machine learning aspects that we've learned, right? You talk about any machine learning algorithm, the tasks are iterative. They're always iterative. You have to read the data frame multiple times, right? Based on the number of records you have, those many times you have to read the data. One record at a time. Right? Now, how about storing this table in the memory? First time when I read it, rather than consuming the data as is, I would put that into memory. Right? So first transaction will become a little lagged because it has to take the data, complete data, and put it in the memory. But from there on, when you're accessing the same table for multiple records, the data is already loaded into memory. You don't have to do the disk read write operations, right? So multiple records which are there in that particular memory block can be read at a much faster rates because accessing the data from the disk would be much faster when compared to accessing the data from your memory. This is the objective of Spark. Now, when I come to the history, right, I told it was made open source in 2010. University, UC Berkeley, that's where the birth of Apache Spark happened. And Apache Spark is developed using a programming language called Scala. Okay, Scala is a programming language, which is also known as a hybrid programming language. It's like it has both object-oriented features and it also has function-oriented language features. Hence, it is called as hybrid language. It's just like your Python. But it is low level. Scala can be treated as a low level programming. It's like Java, as I mentioned. Object oriented can be written. Spark's main objective is the speed, right? So it is fast, interactive in-memory cluster computing framework. Right? It's fast, interactive, and in-memory cluster computing framework. What does that mean? So let's say this is my cluster. I'm drawing a cluster. This is my cluster. So I have a name node. Let's say I also have resource manager in this. Then I have data nodes. Let's say these are my data nodes. Okay. Now what we are doing in Hadoop, we are basically taking the capability of all the hard disks and calling it as HDFS. So this is nothing but physically the hard disk is obtained from these systems, right? Hard disk. This is your HDFS. Now we also have map reduce capability. Hadoop has HDFS and map reduce capability. Right? Now, when I talk about map reduce, we are trying to do processing using map jobs and reduce jobs. So we do process by retrieving the data first from each and every node, right? So that means for map reduce, I am using the processing capability. CPUs, here I'm using disks, processors, right? This is what your Hadoop is using, storage and memory. No, sorry, storage and processing. Now, in Hadoop, we are not consuming the memory of each and every device, right? Let's say each computer has 8 GB hard disk. Okay, assume each computer has 8 GB memory. Sorry, not hard disk, my bad. 8 GB memory. Now, what we do in Spark is just like how we are creating a HDFS, which is a consolidated or concatenated disk space. For Spark, we consolidate the memory. So how many memories, devices are there? 10 devices. Each device has 8 GB memory, 8 GB into 10. So that means my Hadoop cluster environment, which has Spark installed in it, has a capability of 80 GB memory. Yeah? Making sense, guys? Physically, this memory is nothing but blocks of your individual nodes, right? But we map it such a way that we are assuming that all these memory devices or memory basically that we have for all these nodes, we are combining all that memory and consuming it as a single big supercomputer having very high capability of memory. This is exactly what Spark does. So Spark, right, is relying on memory. Hence, we call it as fast, interactive, in-memory clustered computing framework. It is computing, but it is cluster computing. Okay? So here, Spark focuses on speed. Okay, that is the primary objective. Remember I told? And because it is working on distributed environment, it can also scale up. Just like how if you have more requirement, you add more nodes here for Hadoop. Each computer will have memory. So that memory is pulled in and we get higher configuration for the memory from the memory perspective. So it is scaling up, right? The data that we are talking about is actually residing in memory. Okay, that memory, again remember, is physically a small piece, 8 GB for one node, but collectively that memory is very huge, right? So we are saying distributed computing engine. So we are not storing the data, remember, into any disk. We don't do that. We only use the data which is already stored in your HDFS, we or Spark. We pull the data, we take the data which is there on the disk, upload or push it into the memory, which is Spark's memory. And in that memory, once the data is in memory, the processing can be happening very quickly, right? Rather than on disk, processing will become much faster on memory. And it is not going to give any different experience for the end user. End user still imagines that he's working on one single computer, right? And it is very easy to develop. How? I'll talk about it. It basically focuses on speed. It will also allow us to do real-time processing, machine learning, which is always an iterative process, and language flexibility, right? Hadoop gives language, Spark gives language flexibility. What is Spark, guys? When I talk about Spark, what is Spark? How can you define? What do you think? The definition is there on the screen. But can you explain in a very simple terms? Spark is a service, okay. Flash, no, not really, not Flash. We can write programs in it, right? So Spark is like a platform, okay? Here I have multiple computers interconnected. I'm basically taking the capability of all these nodes. So using Spark, you would be able to write the codes. Just like Hadoop. Remember, Hadoop is like operating system, right? Similarly, Spark is also a framework, a platform, which allows, it's like again software operating system, mind you. Okay, it allows users to use the capability of these multiple systems for processing the data in memory. So it's just creating a platform for us. Now on that platform, you might want to process the data, but for processing the data, you can write any language. When I say any, Spark allows 4 different languages. The first one is Scala. It's like mother tongue for Spark because Spark was developed using Scala. Okay, it is developed using Scala. So it supports obviously Scala. Then Scala is basically a low-level language which is very similar to Java. So it also allows or supports Java. Spark also supports Java code. And Scala is like a bridge between object-oriented and functional-oriented, very similar to Python. So Scala is similar to Java and similar to Python. Okay, and because of these similarities, though Spark was initially developed by Scala, Spark could easily understand Java and Python as well, right? Because of the similarity. But of late, later on, R programming was also introduced, right, for this platform because of machine learning capabilities that we have, and R being the best tool for writing machine learning algorithms. R was also introduced to Spark's framework. That means A developer can choose between one of these 4 programming languages to write code for executing on Spark platform. Right? Language flexibility. It has built-in machine learning algorithms. Libraries are there. Right? So this is basically your Spark history or features. Spark is said to be 10 times speed. Right? It can achieve 10 times speeds when the data is getting executed for the first time. That means the data is getting accessed from disk. But thereon, once it accesses the data from disk, from there on, right, the data is getting loaded into memory. So you don't have to explicitly read, right? You don't have to explicitly read the data. Hence, you will get 100 times speed achieved in Spark. If it is an iterative transaction, right, you can achieve 100 times fast speeds. This is a standard, okay? This is benchmark. So if I run a transaction, a program on Hadoop, let's say using PIG or MapReduce framework, the same code can be executed in 100 times less time, 100 times faster, or you can say, using Spark. That means if I basically take 1 minute time to execute a task in MapReduce, the same task can be done in 1/100th minute in Spark. That's the comparison. But first time it is only 10 times. Because first time when it is reading, the data has to be loaded into memory. First it has to get into memory. And that happens from disk only. So you're accessing disk, right? So it obviously will be taking a little while. Now, what exactly happens in Spark? Spark, like Java, is a multi-threaded application, right? And it uses JVM for executing the code. Java Virtual Machine. It is Java environment because Spark code is also compiled. When compiled, it gives us Java classes only. So you use JVM for executing Scala code. So you can imagine executor is like a processor. Okay. Now for this processor, we will have multiple threads. We will have multiple threads. Each executor can have multiple threads. Thread is nothing but a subtask, right? And we generally have threads sharing the same resource. If I have a task, let's say I have a task, this task gets split into multiple subtasks. Each of the subtasks can be handled as a thread. You can imagine that each subtask is a thread. Right? Now, each of this thread can again contain multiple subtasks, I mean, small transactions. Right? Each thread can process multiple tasks simultaneously. Simultaneously, parallelly, we can do that. So you can see the parallelism that we are achieving here, parallel computing that we are achieving here. Right? This is basically context switching. But if you have a Hadoop cluster, that means you have multiple processors, right? Each computer has one processing, at least one processing unit. So when you're executing the data using Spark, you'll have 1, 2, 3, 4, 5, 6, 7, 8 processors. So you can get this right entire transaction at a much higher speeds. Right. So that's the logic of the speed here. It works with the threads, basically, parallel threads. So automatically the speed is achieved. Now we have learned about so many tools, then why again something new? Right? Remember, anything new, that means you'll have a chance to enhance the previous whatever the software that we're talking about, or whatever the product or software that we're talking about. The second versions, third versions, when you are saying, you'll always have a chance, scope to upgrade. That's the reason why we say upgrade in the first place. That means better than what we have already existing. Right? So we already have various solutions. Can I get much better than that solution? That's the first idea. Right? The second idea is the speed. When I do transaction using Apache Pig or Hive or MapReduce, data has to be handled from hard disk only. Right? Data has to be handled from server. So accessing becomes slow, and hence we have the Hadoop ecosystem tools, right? Or you can say Spark coming into picture over Hadoop ecosystem tools because of this one reason. Spark does not convert the data into MapReduce framework. It is a generalized programming framework. Framework, I use that terminology. I'm not saying programming language. Okay, it's not a language. Spark is not a language. Okay, Spark is an ecosystem or an operating system. Right? So when we talk about any of these MapReduce related application, they always have high latency. You already know what is latency, right? Latency is the time taken to get the execution done for a program. From the programming language perspective, that is your what do you call the terminology, latency terminology. Right? Now, when we look at this, Spark keeps the data in memory and it does the calculations at higher speeds. Right? Low latency. These are the reasons why we need to go with Spark, or why Spark is becoming popular when compared to any of the programming frameworks that we have in MapReduce. Speed, guys. Simple. Speed is the reason. So you can see quickly, these are the features. It's open source. It allows, right, to do the computing on distributed and parallel mechanism. Then the computation happens in memory, not on disk. The Spark framework, right, allows interactive as well as iterative applications. It is in fact developed or designed to work in the case where you have iterative transactions, repetitive transactions. This way what happens, the data is lying in memory, so you can very quickly access the data and get the processing done. Right? So that's your iterative and interactive part. Then the data set that Spark works on can be standalone or can be distributed as well. Yes, Spark can understand distributed data sets as well. MapReduce do not allow, MapReduce again in here, MapReduce do not allow real-time processing. It does not allow real-time processing. Right? Whereas Spark allows it. There's something called as Spark streaming. We'll discuss about that. Spark allows real-time processing. And as I mentioned, Spark allows you the flexibility. It allows you to write programs either in Python or Java or Scala or R. Right? So Python allows these programming languages. Because you can also work with Spark on top of Hadoop, right? You don't need specialized hardware for getting your Spark programs executed. The Spark programming can be, or the language can be installed on commodity hardware like Hadoop. Right? Spark is a generalized programming. It does not mean, it means that you don't need a Hadoop. Right? I have Spark installed on my local system also. Right? So that's your Apache Spark. It is used by, right, analysts, data scientists, data engineers, right, data developers, etc., etc., etc. A lot of people use the Apache Spark, especially data engineers, right? Heavily use this. It is also OS independent, right? You can basically develop your application, Spark application on Windows or Linux or Mac. So these are few of the features. So we'll try and understand why Spark, right? When there was a huge concern with respect to handling big data, organization has invented big data Hadoop. Hadoop, which works with MapReduce framework, is used to process this data. It all started in 2004 with a white paper that Google published, and then it became a history. Hadoop became one of the top products or softwares which help organizations to manipulate the huge amount of data that they are generating. But there is a challenge with respect to this Hadoop MapReduce framework. Can anyone tell me what is that? There is a drawback. What is that? Anyway. No? MapReduce is a low-level language. It is low-level language. Okay? That is the first thing. Hence, we have the third-party applications like Pig, Hive, Sqoop, etc. But each of this particular high-level programming abstraction that we are talking about is designed to do a specific thing. Right? So we have so many different applications like this. Drill, Storm, Mahout, S4, GroupX, Thais, Impala, Pig, Hive, etc. The problem in this architecture is that if I need to get, let's say, machine learning, then I'll use Mahout. Right? I know which tool basically I need to refer to. So I'll basically take Mahout. Now, there's another requirement for the same client. Let's say he wants to do, let's say network analysis. Okay. Let's say he wants to, the client wants to also get, let's say something using Giraffe. Okay, some transaction. So what is happening here is, as an analyst, as an employee of that particular organization, you are expected to know Mahout. At the same time, you're also expected to know Giraffe. Right? So if it is one or two, probably it would be very easy to one person learn all the concepts. Right? But we are not talking about just one tool or right one time. Yeah. So it is basically to what I should say to get a specific thing done. Either you hire a person who is familiar with that, or it is basically telling us to train your existing resources with these particular different tools that we have. Now, as a human, how many tools can you learn? You can learn the idea, you can learn that there is something called as Hadoop, there is something called as Spark and all that, right? But you cannot learn and remember everything. That's not possible humanly, right? So this is where organizations wanted to find a solution, right? This is exactly where we had the challenges for big data arise. So as a solution, we are trying to come up with one software which is known as unified engine, right? Generalized unified engine. We want to basically use this particular software or find a solution for our problems using this software. And Spark, as I mentioned, is supporting all this. It is called as General Unified Engine. Okay, you can simply call it as a unified engine, right? So we have Spark coming into the picture. It is trying to help the big data engineers, right? But when we look at the comparison, here I have Hadoop. I'm trying to compare Hadoop with Spark. Yeah. For Hadoop, we have map reduce. Here we have Spark. Then we have Yarn. This is cluster manager. This is processing component. So if you look at Spark, do I have any cluster manager? No. For Spark, we do not have any inbuilt custom, right? I should say the software, Yarn, cluster manager. Hence, what we do, we use Spark on top of Hadoop. We deploy Spark on top of Hadoop and we take the advantage of the infrastructure that Hadoop gives us, right? So that's about cluster manager, Yarn. Then you see the actual storage on Hadoop DFS. That's the distributed file system, right? So this is your first comparison that we need to do. Later on, we can do other things. So for Spark, right, we have, I should say, the unified engine. Spark has the unified engine, which allows the processing of the problem, right? The problem statement that we are seeing. So you can say safely that your Apache Spark is only replacing MapReduce framework for Spark, not the entire Spark, right? So we can basically take full version here. This is the comparison, because when I talk about, let's say, structured query language, right? You can see that Hive is used to handle structured data. Whereas here you see Spark SQL is basically used for structured query processing. We will deep dive into this again. Then if I have to do machine learning on top of big data, then in Hadoop, we have a third-party tool called Mahout. In Spark, we have machine learning library module. On Hadoop, if I have to do real-time data processing, we have Storm. In Spark, we have streaming component. Right? Like this, we have different components in the same software. So as an organization, you will want to try and find out a person who's familiar with Spark. Right? That's it. right? You don't need to learn so many softwares. Yes, Ashna.
So, sir, for example, we have Mahout, right? And then we have Sparks M library. So the syntax is the same for these two, or it's different?
Completely different.
Completely different.
Mahout is a separate tool. Machine learning library is a separate tool. This Mahout is on top of Hadoop, whereas MLlib is
Top of
Spark
the Spark.
capability.
But on the framework of the big data, we have the Sparks on top of the Hadoop, right? The ground layer is Hadoop. On the top of the Hadoop, we have the Spark.
That's
so
correct.
it becomes redundant.
No, why?
Because we in the top of the Hadoop we have Mahout, right?
Okay. See, if I have Windows operating system, right, Ashna?
Mm-hmm.
In that Windows operating system, I can have multiple softwares installed.
Yes.
Now I can use Word document to read a text file. I can use Word document. I can use text file. I can use Notepad++, different additional
Oh,
softwares.
okay.
So Mahout is like these different softwares that we have, right? Mahout is one specific software which allows to do machine learning. So if
Now
you
understood, sir.
choose to install, you will install it into Hadoop.
Mm-hmm.
Okay, but if you don't want, you'll not have that. So it is not redundant. You'll just not use Mahout. That's it.
Oh, okay. Thank you, sir.
Yeah. Next slide should give you an idea. Comparison with Hadoop. Okay. See, Hadoop basically is a software which has distributed framework, right? Spark also is said to have a distributed framework. That's the reason why we are comparing these two. In Hadoop, we have two components. One is with respect to storage. The other one is with respect to the processing or computing. Whereas in Spark, you'll not see storage component. It is only compute. So if I have to work with Spark, I need data. So where is that data lying? You can say HDFS. Right. So if I go back to the previous slide, if you look carefully into this chart, this is basically what you have to look at, not the entire thing. This is what you have to compare. So we are comparing Spark with Hadoop, right? Now yarn is remaining yarn. HDFS remaining is HDFS only. But one thing that is changing is from MapReduce, we are changing to Spark. Right? So I will not use that. I will use Spark capability. Because Spark does not have storage capacity. So it has to rely to some of the storage devices. Why not Hadoop? Because Hadoop also has distributed environment. Spark uses the same hardware. Right? And in Hadoop, when you do the compute, it always has to go with map reduce framework. Map and reduce. Whereas Spark is a generalized computation framework. It is not looking into partitioning and all that. Partitioning is here also. Partitioning will be there here as well, but it is not working on the same lines of map and reduce. Right? You directly apply the logic, whatever is the logic that you want to achieve. Then Hadoop is not designed for iterative work because every time it has to access the data, it has to access the physical disk. So disk IO happens, that's where the delay comes in. Right? Whereas for Spark, if you see, it is specifically designed or developed for doing machine learning. Spark was specifically used for machine learning, and that's it. That's where it is very popular. Hadoop is used only for batch processing. It cannot be used for any other real-time processing, but Spark can be used for real-time also. Language flexibility. In Hadoop, if I talk about MapReduce, it is just one software and you have to learn low-level coding. Right? MapReduce is also a framework and you will have to write either Java or Python or Pascal, right? This kind of a low-level languages. And if you want to use high-level coding, then you'll have to use new syntaxes, new ways, basically, to write that code. Whereas in Spark, it is upright saying it allows Java, Python, Scala, and R. This is the benchmarking with respect to Hadoop. So when Hadoop was launched and when Hadoop was being used, Hadoop created this world record. We're talking about 100 terabytes of data getting processed, right, by 21,000 nodes. 21,000 nodes, right? That means I'm using 2,100 computers which are interconnected, and this setup took 1 hour time to process 100 terabytes. Using your traditional systems, you cannot even imagine to process that data. Right? It will take ages. But Hadoop solved it or processed it in 72 minutes. 2,100 nodes, 72 minutes. Now, if I look at this, this is a world record, right? Now, when Spark was launched and Spark was being verified for 100 TB, it took only 23 minutes. That means less than half. I mean, look at that. 72 minutes, 23 minutes. Right? Huge reduction in the effort. But you should not just look at the time. You should also look at the number of nodes that are used. Yeah? So only 206 nodes are used. Whereas in Hadoop, we use 2,100 nodes. It's a huge difference, right? So the world record has been beaten down like anything. Right? And when the experiments were conducted, so it is observed that Spark grows linearly with respect to the processing requirements. So this is about comparison of Hadoop and Spark. Cores, okay, your computer has cores, Abhishek? How many core CPUs your computer? We generally say 5 core, i7 core, i8 core, i9 core, right? Those cores I'm talking about. Yeah. Reducers are your MapReduce jobs. These are transactions that parallel transactions that get executed to get the results. Yeah. Now, when you try to do a transaction on HDFS, this is your disk. So when you're trying to access data from disk, you're doing a disk IO. Here, you will basically be doing map jobs to pull out or retrieve the relevant data that is required. Okay, this is the first step. Then again, we look at the disk. That means the intermediate data that is getting created by map jobs, right, are getting stored in HDFS. Right, it is getting stored on HDFS. Now, once this data is recorded here, when I say data, it is the output of map jobs data, which is nothing but data accumulated, or you can say intermediate key value pair, which is accumulated by the master, so that this can be passed as input, right, disk IO happens, and you're passing the data as input to reduce jobs. Yeah, you're passing this into reduce jobs. Then you have IO again, and here we again have disk. So look at this, 1, 2, 3. So you are doing 1, 2, 3, 4. 4 times you are reading the disk. Input output. So obviously it will take a lot of time to process that. But look at the flow of Spark. The first time when we are trying to read the data from the disk, here the disk read write happens, right? We are reading the data. But where is it posting? It is posting in the memory. Now, once it is in the memory, you don't need to do disk I. So let's say here you are doing intermediate transactions, right? So again, you have memory here. And on this intermediate results, we want final transaction done. Final transaction. So what is happening here? This, when you do the final transaction, the result that you're going to get is getting published here. If you want to store, you can store it. But otherwise, here, the I basically symbolizing that you are watching, you're seeing the result. Whereas here you cannot see, you have to first store the data. So how many disk IOs are happening here? Here, one disk IO, maximum you can think of having 2 disk IOs. One here and one here if you want to store the data. Right? Now, because I don't have discrete rate operations, the entire flow becomes much quicker. And this is basically the framework, or you can say the architectural diagram of Spark, which is residing on Hadoop. When we say Hadoop, remember it is the disk that we are talking about, disk. This disk is nothing but the combination of all the data nodes. Right? So we have data nodes, and on top of that we have HDFS. This is the disk. Now on Spark, in Spark, remember Spark is also a distributed framework. We're talking about Spark being distributed framework. Right? That means each computer is getting split, or each node is getting segregated. Right? Now, if I want to manage Spark applications, then we need a master, right? In short, it is master-slave architecture that we are talking about. Right? It is the master-slave architecture. Right? Now, the master in Spark is known as Spark driver. This marked in yellow, this is your master. And the slave components that we have, you'll have multiple slaves, multiple data nodes. These are called as the worker nodes. Master is driver, the slaves are workers. You can just imagine like your data node or node manager, we have one Spark worker residing in one node. But underlying data is HDFS only, guys. Physically, the data gets stored into this file system, right? So we are accessing that data. So what happens when a client makes a request? A client wants to execute an application So that application goes to the driver program, master. Now this master will be responsible for scheduling, for task assignments and everything. But how does a master know which node to be picked up? There are multiple nodes in the cluster, right? Which node should be picked up for executing these applications that the client is requesting or the customer is requesting? So what we do here, we make the subtasks based on whatever we understand, but driver program, the master program, is going to connect with cluster manager, because cluster manager actually keeps track of the topology and the load on the servers, right? So cluster manager basically gives the information to Spark master, and this master would segregate the transactions to these worker nodes. Yes, Ashna?
Sir, the cluster manager, is this on the underlying of Hadoop or the cluster manager for the Spark?
Cluster manager can be either from Spark side, or we can use Yarn, which is the Hadoop cluster cluster manager, or you can also use any third-party cluster managers.
Okay. So it's not Spark dependent cluster manager. So it can be
Yeah,
like, okay, thank you, sir.
it's not dependent, right? Because cluster manager that we are talking about will have metadata. Remember, it knows the entire topology, it knows who's working what and all that. Hence, the master, the driver program, interacts with the cluster manager to understand.
Thank you.
Ashner, you are not on mute.
Sorry.
Yeah, so cluster manager keeps the track of the information. That information is shared with master, and master decides which node executes what task, right? So each worker node has executor, right? This is a single JVM. Again, Spark also is using JVM, right? It is like, I remember I said it is developed using Scala, which is nothing but Java. In a way, it is nothing but Java. So we need JVM here also, because the code that we are getting executing, the code that gets executed on Spark, it has to be processed using Java files or Java class only ultimately. Right? So we need JVM. For each node, there will be one executor. One executor is nothing but one JVM. And within that executor, we have multiple threads. Right? One task can be imagined as one thread here. Right? And your worker node processes this data and shares the information back to the master. And master accumulates the entire data and shares with the, gets the result basically. So master is responsible. It is responsible to send the task to the slave nodes, that is your worker nodes. And these worker nodes, once the processing is done, they send back the results to the master. For the first time, the data will be on the hard disk, and later on it is moved to memory. Yeah, so that's basically your Spark. Now this is the unified tech stack engine of Spark. We call it as unified engine. It's like combination of multiple things. The first and foremost layer that you need to see is the Spark core. Right? We are saying for Spark, this is the core, right? Like the name suggests, it's the core component. Right? And remember, Spark is only computing engine. It doesn't have storage engine. Like Hadoop, we have both. In Spark, we don't have both. Spark is competing with MapReduce framework. It is only a compute engine, right? So in Spark, we have this data frame or data frame API, or you can say data API, data source API, which will allow Spark to interact with many data sources. Look at those examples. You can talk about Hadoop, you can talk about various other softwares, you can talk about standalone files, you can talk about data lying on cloud. So like this, you can see Spark allows or understands to read the data from various softwares. SQL, NoSQL databases, physical locations, physical files, right? Big data platforms, all these. So that's about your Spark core component. Now Spark core does a lot of things. We'll discuss each component in detail. Next slides, we'll brief them out. Then we have data frame API. Now, what is the default data abstraction in R and Python? In R and Python, how do we deal with data? It's a two-dimensional data, right? Abstraction. It is like table. What is it called as? Data frame. Yes, it's called as data frame. Very good. So R and Python understands data frames. What does SQL understand? SQL, data, table. What does your Excel understand? Excel understands something called as macros, spreadsheets, right? Spreadsheet, exactly. Something called as macros sheets. So if you see, each tool has a standard, right? They try and understand a specific type of data. So in Spark also, we have a very, very special type of data, which is called as RDD. We call it as data frame API is provided in Spark core, which allows the data to be read from these different sources and then convert that into something called as RDD, resilient distributed data sets. What does that mean? We'll talk about it again. As I mentioned, we're trying to read each and every component, right? So these are the first two layers. First one is the Spark core, which basically lays the foundation for our Spark. Then we have RDD, data frame API, right? RDD. Next layer, we have these capabilities of Spark which allow us to do the processing. So there are four capabilities, important capabilities, plus Spark core, total 5. If I want to do queries, structured data manipulation, then I use this, Spark SQL. If I want to work with live streaming data, Spark streaming. If I want to develop machine learning algorithms, then MLlib. If I want to do network analytics, then I will do graphics. Finally, to achieve all this, we need packages, and Spark gives us inbuilt packages module. A lot of packages are readily available for us to do the processing. And so this is how you can imagine the structure or architecture of your Apache Spark. Now you can see that on the top, you have 4 different languages, the symbols, Python, R, Java, Scala. Right? Any one of these four can be used for processing the application or developing the code. You can either use any one of them to write your programs. On cloud, majorly it is PySpark. Now, Spark Core, if I have to deep dive and try and understand this, Spark Core is the core component of your entire Hadoop infrastructure. Hence, it's called as core. It contains the basic functionality of Spark. It includes components of basically the Spark coding. It also allows you to schedule the transactions. It allows, or it is capable, I should say, to manage the memory. It identifies which transaction failed and why. And based on that, it tries to recover. It is interacting software. I mean, you can write the code interactively. Spark code, it is interactive, right? And then trying to access the data also. From different sources, it is trying to read the data, right? It interacts and reads the data. So these are various capabilities in your Spark core. It's just like your name node service, right? It's the core component. Remember, it's the fundamental component of your entire foundation component of your entire Spark. Now, it also has a lot of APIs. Here we have something called as RDD. These are database API. It's called as a database API, which converts the data into RDD, resilient distributed datasets. What does that mean? Again, we'll try and understand. So this is your Spark core definition. Then we have Spark SQL. Originally, it was called as Shark. It was initially called as Shark. Spark SQL is basically allowing us to deal with structured data on big data environment. Right? Now we have seen HDFS, we have seen HBase. Prior to that, we have seen your Hive. So all these languages, especially Hive, if you see, it is allowing you to work with structured data, right? So it also has Hive capability. Spark SQL has Hive capability also, where Hive is nothing but a query language which allows you to handle the structured data. We call it as HQL, Hive Query Language, right? Shark was the name for older version for having SQL on top of Spark. The old version was Shark, right? Next, now we have Shark basically is replacing that Spark SQL, right? It is replaced, and then we have Spark SQL. The Spark SQL has capability of both SQL queries as well as HQL queries, right? So it's a combination of both Hive and, or I should say, Hive's query language and SQL, structured query language. So if you want to work with structured data, go with Spark SQL. Then streaming data, as and how the data gets generated, you might want to work on that new data on the fly. So Spark streaming basically is a component which allows us to work with the live streams of data, right? Server log analytics is done using that. Of course, at scale when we do, we use Spark capability, but if it is in a local system or if you're doing it for regular systems, then standalone systems or standalone components are good enough. And for that, you can use Python. You don't need Spark. Yeah. So these are the examples, basically. Log files analysis, then web server records number of hits. Twitter, as and how people start writing something, you might want to process that. So various such applications can be thought of where Spark streaming can be used. Then we have ML. But this is something that I don't have to explain. ML is nothing but machine learning. We have structured and unstructured, we have supervised and unsupervised capabilities, regression and clustering and classification capabilities inbuilt, right? So ML-lib is nothing but machine learning library. All the machine learning related libraries or functionalities are basically available in ML-lib. You'll be doing all those right ML capabilities. Then GraphX is used to manipulate the graphs. Right? It's like network analysis. All right. So it basically allows graph like data to get the computation done. Network analytics. Right? All these components that we talked about, they work with Spark RDD. Right? Of late, the latest versions of Spark, they started allowing, or the architecture is designed in such a way that Spark can also read data frames. Right? So we can basically say Spark RDD is the first level of API. I mean, that's the granular level. Now the same logic has been upgraded. Because when we talk about machine learning, we prefer using R. For machine learning, statistical computing, R is preferred. And R understands data frame, right? You need to have the data in a table representation. So that can be done using graphics. Okay. Then we have Spark Shell. And then we have these building blocks. I'll talk about building blocks later, but yeah, this is the interface. Spark Shell is the interface. Like in Linux, we have terminal, right? When you want to type something in Linux, you type it in terminal, right? Similarly, when you want to type Python code, you will have Python shell, Python console, right? Isn't it? Python shell or Python console, sorry. Same way, if you want to work with Spark, then you need to have an interactive medium, isn't it? For Java, there is no interactive medium, right? Java is not interactive. Java can be written on Notepad and then compiled it and all that. But if you talk about Scala or you talk about Python, we have dedicated shells. For basically for Scala, we have Spark-shell, right? Spark shell. Then we have, for Python, we have similar shell. We call that using PySpark library. The command for Spark is PySpark. The command for Scala is Spark shell. And this is how you will see, it's like a command prompt. And you'll be typing your code in this, or you can also use Spider interface to configure, to connect with Python. If you connect it, basically Spark with Spider or Jupyter Notebook or any other interface. Ultimately, you need to have a interactive medium where you can type your code. And for R, we have R console, right? So all these things can be implemented, and you will be writing your code in these shells or consoles, and the execution happens basically by the Spark engine. This is the interactive interface, right? Whether it is deployed on cloud, whether it is on local system, whether it is on on-premise cluster, could be anything. But your shell would help you to interact with these basically the infrastructure. So this is basically how the shell can look like. We will see PySpark also. And then we'll work with PySpark. We'll not work with Scala. It's our, let's say it's out of scope. But we will be using PySpark to do these things or executing things. Right? Any questions still here? Do we have any questions? Pretty much straightforward. Anyone has any questions, please? Okay. Do you want me to continue or shall I take a pause here? I'll leave that choice to you people. Okay. That response was quick. Okay, sure. I know, it's too much of concept, too much of theory. So that's the reason I'm asking you people. And I want you people to focus very clearly on these building blocks. Okay, so let's do this tomorrow only. And installation will also be covered tomorrow. We'll start with Spark core commands. Okay, tomorrow we'll do that. All right, guys. Then, yeah. Yes, we will install that tomorrow. It's not going to take much time. It's like Apache Pig. Downloading will take time. We'll do that as soon as we connect tomorrow. Because we have some theory to cover and we'll be able to download it. It's around 150, 200 MB data, maybe, roughly. So we should be able to download it. Yeah. Okay, guys. So, all right, we'll connect tomorrow. Good night, everyone.